Today we are going to deal with canal faults. Canal fault means it's an irrigation structure which is constructed across a canal. So canal fault is an irrigation structure which is constructed across a canal, and it serves for two purposes. The first one is to lower its water level, to lower the level of water. Canal fault means it's an irrigation structure which is constructed across a canal, and it serves two purposes. First one is to lower the water level. And the second one is the main function to destroy the surplus energy. That means to destroy the excess energy which is liberated by the water, which is liberated by the falling water, which may otherwise cover the beds and banks of the canal. That means first one is to lower the water level, and the second one is to destroy the excess energy of the falling water. To destroy the excess energy of the falling water. Otherwise, what will happen is that particular water, that particular falling water will scour the beds and banks of the canal. Scour means it's the flushing effect of water, or the flushing action of water is termed as scouring. So canal fault is an irrigation structure which is constructed across the canal. It serves for two main functions. The first one is lower the water level, and the second one is to destroy the excess energy which is liberated by the falling water, which may otherwise, if it is not destroyed, if the surplus energy is not destroyed, that falling water will scour the beds as well as the banks of the canal. So that's a canal fault, and these are the two main functions of the canal fault. Now we can see what are the different types of canal faults. Types of fault: the first one vertical drop fault, second one ogee fault, third one rapid fault, fourth one stepped fault, and the fifth one is notch fault. We can see first one is vertical drop fault. In case of a vertical drop fault, it consists of a vertical drop wall. That is, the vertical drop fault consists of a vertical drop wall and a cistern. You can see the upstream region and the downstream region. We know the water is flowing from the upstream region to the downstream region, and the water flows over the crust segment. And after flowing over the crust segment, the water falls into a cistern. And in that cistern, the cistern is a portion where the surplus energy of the water, where the surplus or the excess energy of the water, which is leaving the crust. That is, you can see that the movement of the water is from upstream to downstream. It's clear. So the water moves from the upstream, then towards the crust, then the water comes to the cistern, and afterwards to the downstream region. So the excess energy of the water, which is flowing over the crust, is destroyed when it comes in the water cushion. That is, this particular region is a cistern, and it provides a water cushion. The function of cistern, that is, the function of the cistern is to destroy the surplus energy or destroy the excess energy of the water which is leaving the crust segment. That is, destroying the excess energy of the water which is flowing after the crust segment. That is a function of the cistern. And you have learned about the design and drawing of Sarda type fault. The Sarda type fault is a kind of vertical drop fault. Okay, so Sarda type fault is a kind of vertical drop fault. So I hope we have clear about vertical drop fault. You can see an upstream segment, downstream segment, and this is a crust. The water flows over the crust towards the cistern, and in the cistern, the excess energy of the water which is flowing over the crust is destroyed. Now, the second one is ogee fault. Ogee fault means it consists of gradual convex as well as concave curves. That is, you can see in the picture, it consists of several gradual convex as well as convex curves so as to provide a smooth transition. That is the ogee fault. In the picture, you can see it consists of several convex as well as concave curves so as to provide a smooth transition and to reduce the disturbance and impact. It consists of smooth, convex as well as concave curves so as to provide a smooth transition of water so that we can reduce the disturbance and impact. That is about an ogee fault. And this photograph shows an ogee fault. It consists of gradual convex and concave curves to provide a smooth transition of water. Now next one is rapid fall. Rapid fall consists of a glacis which is sloping, which is having a slope between 1 in 10 to 1 in 20. That is, you can see that it has a slope ranging between 1 in 10 to 1 in 20, and in the picture you can see that the rapid fall is having a slope of 1 in 15. The picture is clear, it is having a slope of 1 in 15. And the slope can range between 1 in 10 to 1 in 20 for a rapid fall. It consists of a glacis with a sloping, and the slope ranges from 1 in 10 to 1 in 20, that is between 1 in 10 to 1 in 20. And in the picture you can see a slope of 1 in 15. Next is a photograph of a rapid fall. The slope can range between 1 in 10 to 1 in 20. Next, third one is stepped fall. Stepped fall means it's a development over rapid fall. That is, it's a modified form of rapid fall. You have seen rapid fall. This is a rapid fall. And the coming is a stepped fall. You can see that the stepped fall is a development over rapid fall. Or we can say it's a modified form of rapid fall. But it's one of the defect is that its construction cost is higher. It's a modified form or rapid fall and its construction cost is higher. The photograph shows a stepped fall. Next is a trapezoidal notch fall. A notch fall, we have learned about the trapezoidal notch fall. We have learned the design, the theory part and the drawing, etc. in the previous class. The trapezoidal notch fall. Next is Sarda type fall. That I have explained that Sarda type fall is a kind of vertical drop fall. Sarda type fall means it's a kind of vertical drop fall, and it was introduced. It was introduced to replace a notch fall on the Sarda canal system in Uttar Pradesh. It's a kind of vertical drop fall, and it was introduced to replace a notch fall on the Sarda canal system in Uttar Pradesh. And talking about the design of a Sarda type fall, the first step is the design of the crust. So you can see that the two types of crust are used. Two shapes of crust are used, and one is trapezoidal crust and the next one is rectangular crust. Okay, so when you have learned about the design, I told you that we are using two shapes of crust walls, and one shape is trapezoidal shape and the next shape is rectangular shape. You can see that why we are using trapezoidal and rectangular, that there are several criteria, and the first one is the discharge is less than 14 cumecs. That is, if the discharge is up to 14 cumecs, we can use a rectangular crust. And if the discharge exceeds 14 cumecs, we are using a trapezoidal crust. Okay. So the first step is a Sarda canal system means it's a vertical drop fall, and it was introduced to replace the notch fall on the Sarda canal system in Uttar Pradesh, and two types of crust walls are used. One is a rectangular crust and the next one is trapezoidal crust. We are using a rectangular crust when the value of discharge is below 14 cumecs, and we are using a trapezoidal crust when the discharge value exceeds 14 cumecs. As you can see that when Q is less than 14 cumecs or when Q is up to 14 cumecs, we are using a rectangular crust. And when the value of Q exceeds 14 cumecs, we are using a trapezoidal crust. That is about the design of crust. It's the first step in design of crust. We are using two shapes, trapezoidal and rectangular. I hope you have understood the situation where we use a trapezoidal and where we use a rectangular crust. And the second step is design of cistern. I have told that the cistern means is a place where the surplus energy of the falling water is destroyed. The cistern is a portion where the surplus energy of the water leaving the crust segment, the surplus energy of the water leaving the crust segment is destroyed or it is dissipated, and the length as well as depression of the crust wall is cistern is given by several standard equations. As the length of the cistern is given by E into HL raised to 1 by 2, the whole multiplied by 5, And the depth of the cistern is given by another general equation, E into HL raised to 2 by 3 into 1 by 4, where E is the difference between upstream total energy line and crust level. So the first step is design of crust. We are using two shapes, trapezoidal and rectangular. The second step is design of cistern. Cistern means a portion where the surplus energy of the water leaving the crust is destroyed, and the length and depression, length and depth, or the length and the depression of the cistern is given by standard equation, and that standard equations are the length of the cistern is equal to LC is given by E into HL raised to 1 by 2 into 5, and the depth of the cistern or the depression in the cistern is given by E into HL raised to 2 by 3 into 1 by 4, where E is the difference between upstream total energy line and crust level. Okay, next step is, so that's about step 1 is design of crust, and second step is design of cistern, and the third step is design of impervious floor. Okay. The total length of the impervious floor is determined using Blythe Street theory. You have learned about the Blythe Street theory and you have done several problems regarding Blythe Street theory. And you know the total length of the impervious floor is determined using Blythe Street theory. And the floor thickness, okay, the total length of the impervious floor, that is, the total length of the impervious floor is determined using Blythe Street theory, and the floor thickness is checked. We are checking the floor thickness using Gauss-Law's theory. Okay, we are checking the floor thickness using Gauss-Law's theory, and the total length of the impervious floor is determined or designed using the Blythe Street theory. That is about the third step. Next we can talk about the protection works. When it's talking about the downstream protection, it consists of bed pitching, side pitching, downstream walls, and energy dissipators. That is the downstream region. And in the downstream region, we are giving downstream protection works. And the downstream protection works includes the downstream bed pitching. You can see here the downstream bed pitching, side pitching. You can see the side pitching, downstream bed pitching, downstream links, and energy dissipators. The energy dissipators are not provided for small discharges. So here we know the value of discharge, but the value of Q is greater than 14 cumex. So we are providing a trapezoidal crust, and here we know the discharge is more. So energy dissipators are provided, but energy dissipators are not provided for smaller discharges. For smaller discharges, we do not provide energy dissipators. For higher discharges, we provide additional dissipators. Okay. For smaller discharges, we do not provide any energy dissipator, but for higher discharges, we are providing energy dissipators. And the energy dissipator consists of 2 rows of friction blocks. Here you can see that, see 2 rows of friction blocks. You can see the friction blocks here, the plan as well as in the longitudinal section, you can see the friction blocks. It is not provided for smaller discharges, but for higher discharges, we are providing friction blocks, and the energy dissipator consists of 2 rows of friction blocks in the cistern and 2 rows of Q blocks just at the downstream of the impervious floor. Okay, so it is not provided for smaller discharges. You can see the friction blocks here. See the plan as well as the longitudinal section. Here you can see that in the plan you can see the friction blocks and the Q blocks. So similarly in the longitudinal section also you can see it. So it is not provided for smaller discharges, but for larger discharges, we are providing additional dissipators. And this dissipator consists of rows of friction blocks. You can see that rows of friction blocks, or else it consists of Q blocks just at the downstream of the impervious floor. Friction blocks at the cistern or Q blocks at the downstream of the impervious floor. Okay. That is about the downstream region. Now we can talk about the upstream region. So we come to the upstream region, and here is the downstream region. So upstream region, we can talk about the design of the upstream approach. The upstream approach consists of wing bolts. Here you can see the wing bolts. These are the wing bolts. Okay. And for discharge up to 14 cumex, that is if the discharge is less than 14 cumex, it is splayed at an angle of 45 degrees. at the upstream edge of the crust wall. Okay. So if the discharge is less than 14 cumex, the discharge is less than 14 cumex, the upstream wing walls, the discharge is less than 14 cumex, the upstream wing walls is played at an angle of 45 degree. ഇവിടെ discharge 14 cumex-നേക്കാൾ കൂടുതലാണ്. Okay, so remember it. Here the discharge is greater than 14 cumex, but I'm now talking about if the discharge is less than 14 cumex. That is, if we are providing a rectangular crust, we are talking about the first case, that is a rectangular crust. That is, if the discharge is less than 14 cumex, the upstream wing walls, you can see the upstream wing walls, the upstream wing walls is played at an angle of 45 degrees. It's played at 45 degrees from the upstream of the crust wall. Okay. Here you know the discharge is above 14 cumex and we are providing a trapezoidal crust. And if the discharge exceeds 14 cumex, if the discharge is greater than 14 cumex, they are curved from the upstream edge. They are similarly curved, but it is given an angle of 60 degree. As you can see here, it is given an angle of 60 degree. If you see the picture, it is given an angle of 60 degree and at a radius of 5 to 6 times h. Okay, it is given an angle of 60 degree and it is given a radius of 5 to 6 times h. Then the discharge exceeds 14 cumex. You can see there are two cases, the discharge less than 14 cumex and the discharge exceeds 14 cumex. When the discharge is less than 14 cumex, it is given an angle of 45 degree. Okay, when the discharge is less than 14 cumex, it is given an angle of 45 degree. And if the discharge exceeds 14 cumex, we are giving an angle of 60 degree. 60 degree, subtending an angle of 60 degree, and the radius is, you can see it is 5 to 6 times h. Okay, that is about the upstream approach. So these are the main steps. First one is the design of crust wall. I talked that there are two types of crust, rectangular as well as trapezoidal. And when the discharge is less than 14 cumex, we provide rectangular crust. And when the discharge exceeds 14 cumex, we provide trapezoidal crust. Next is design of cistern. That is, the cistern is a portion where the surplus energy, where the excess energy of the water leaving the crust is destroyed. And the length as well as depression of the cistern is given by general equation. That is LC. The length of cistern is given by E into HL raised to 1 by 2 multiplied by 5. And the depth of the cistern is given by E into HL raised to 2 by 3 into 1 by 4, where E is the difference between upstream total energy line and crust level. The third step is design of impervious floor. The total length of the impervious floor is designed using Blythe's creep theory. And the floor thickness is checked. We are checking the floor thickness using Colesla's theory. We have learned about the Blythe's creep theory and Colesla's theory in the previous modules. And I hope you are clear with it. Okay. Then next one is that we are talking about the downstream protection as well as the upstream protection. For the downstream protection, we are providing downstream bed pitching, side pitching, downstream wings, and energy dissipators. You can see the downstream bed pitching here. You can see the side pitching, downstream bed pitching. Okay, and downstream wings. These are the downstream wings. It is given as play of 1 in 3. This is the upstream wing. The segment is the upstream wing, and this is the downstream wing. This is the upstream wing, and this segment is the downstream wing. So the downstream protection consists of downstream bed pitching, side pitching, downstream walls and energy dissipators. And these are the energy dissipators. There is several friction blocks and Q blocks you can see in the figure. You can see several friction blocks as well as Q blocks, and energy dissipators are not provided for smaller discharges. But here we know the discharge exceeds 14 cumex and the discharge is more. So we are providing energy dissipators, and the energy dissipators, additional energy dissipators are provided for larger discharges. And the energy dissipator consists of two rows of friction blocks. You can see two friction blocks here. That is, it consists of 2 rows of friction blocks in the cistern. In the cistern, it's the cistern region, and in the cistern region, you can see 2 friction blocks, or it consists of Q blocks. You can see Q blocks, which is at the downstream of the impervious floor. So you can see that it consists of friction blocks in the cistern or two rows of tube blocks just at the downstream of the impervious floor. Okay, that is about the downstream region. Next, talking about the upstream region, talking about the upstream approach or upstream wings, you can see if the discharge is less than 14 qmax. If the discharge is up to 14 qmax, it is subtending an angle of 45 degrees from the upstream of the crust wall. Okay, but here we know the discharge is above 14 qmax, so we can see that they are curved and it is subtending an angle of 60 degrees. You can see here is subtending an angle of 60 degree. You can see it is subtending an angle of 60 degree and it is having a radius of 5 to 6 times h. Okay, now we can watch a video which provides you more information about a canal fault. So all of you please watch the video, okay? Now you can see they are in the videos you can see the upstream region, downstream region, the crust segment as well as the upstream wing walls. Okay, I repeat, in the videos you can see the upstream region, downstream region, crust segment and the upstream wing walls. So you can see this is the upstream region. Okay, the water is flowing from the upstream region to the downstream region. So the water flows from the upstream region towards the downstream region. That is, the water begins to flow from upstream to downstream. Okay, that is, the water is flowing from the upstream region to the downstream region. And here you can see this is the cluster segment. Okay, here is the upstream region, this is the cluster segment, and this is the downstream region. The water is flowing from the upstream. Here, this is the upstream region. Okay, this is the upstream, and the water flows from the upstream towards the downstream region. And here you can see the cluster segment. So you watch it. So this is a cluster segment. And this is the upstream wing walls. This is the crust. Here is the upstream. Here downstream region, the water flows from the upstream region over the crust segment, and the energy of this falling water is dissipated in the cistern region. This is just to understand the phenomenon of a canal fault. Okay. This is a crust. From the crust, the water flows towards the cistern, and in the cistern, the surplus energy or the excess energy of the falling water is dissipated. So at these regions, we can also provide steps. Okay, at these regions, that is what is shown in your plan. In the plan, you can see some steps there. And this is the upstream approach, and these are the upstream wing walls. From the video, you can get just an idea about the canal faults. That is what I hope. You can see this is the upstream wing walls. This is upstream region, and this is the upstream wing wall. We have told that it is not always, it is not straight, it is curved in plan. Upstream wing walls. These are the upstream wing walls. So you know the water flows from upstream region. Here there's upstream wing walls, upstream approach. Then the water is flowing from the upstream towards the downstream of the crust segment. There's a crust. And from the crust, the falling water moves to a cistern. In the cistern, the surplus energy is liberated or it is dissipated.